at this point, it is better that what I am stating just लिखे just line and लिखे that will be the best thing to do. So what we are trying to learn today is learn Einstein's equation. This recording is not starting. So the gravitational potential phi of x satisfies the Laplace's equation. So if I call this my gravitational potential, so this satisfies the Laplace's equation in regions free of any gravitational sources, masses. Okay. The potential this will satisfy Laplace's equation. And in regions where there are sources, the equation will be where this rho basically describes the matter density in the given region. So this we already know. This is the same two equations also arise in electrodynamics, standard equation. So here, this phi is the gravitational potential. This describes the gravitational field. So if there are no sources, if the Laplace is sources, by sources we mean that there are masses, the gravitational potential will be described by this Poisson's equation. Our aim today is to find some equation in curved system for the gravitational field. Now, what do we know? What is the object that describes the gravitational field? Curved system. That we already know. That is the metric tensor. GAV describes the gravitational field. So our main aim today is to find an equation for GAV. That is what we want. So this describes the gravitational field. It curves system. And therefore we want to find equations for this. And obviously these equations, if at all we can find equations for GAV, these equations should reduce to this equation in the appropriate limit. This is the Newtonian gravity equation. So in the Newtonian limit, if at all we can write any equation for GAV, this equation should reduce to this equation. That is a consistency check that your equation is correct. So let us proceed. How can we find out an equation for GAV? First of all, if you note that from this equation is a second order equation, right? In the gravitational field. So obviously, one would expect that if we know that GAV describes the gravitational field, so these equations should also be second order. Okay. So these should be second order differential equations, and which in the appropriate limit, Newtonian limit, will boil down to these equations. And how many equations will be there if we consider that this describes the gravitational field? What is the number of equations that one would expect? Huh? This is symmetric, so we will expect that there are 10 differential equations, second order differential equations. And also, all these 10 differential equations should be tensor equations because these are tensor. So these are the criteria by which one should construct the equation. Since JV is a tensor, so all the equations that you expect to write should be covariant under a general coordinate transformation. These should be tensor equations. Let us now write the geodesic deviation equation. So now we shall consider the geodesic deviation equation, and this equation we have derived in the class previous lecture, and the equation is of this form. Right? The geodesic deviation equation. So it basically tells you that you have, you can go through the derivation of this equation on the notes. But if you have some geodesics like this, which are parameterized by tau, and these are some infinitesimally closed geodesics, so in this direction tau increases, and this is a line. On this line, all these geodesics are at the same tau. So these geodesics are basically differentiated by the parameter h. So a coordinate here, to take a coordinate, to take a point of this geodesic, so this will be described by these two parameters. So what is VA? VA is the deviation vector between the successive geodesics, and this deviation vector basically satisfies the differential equation of this form. So how does this deviation evolve with the parameter tau in this direction? And you can see that if this evolution of this deviation vector with this parameter tau is governed by the Riemann curvature tensor. So if there is a non-zero Riemann curvature tensor, then you can see that this will change, right? This is the evolution equation. So let us start from this equation, and now let us write it down. Let us consider this VA to be delta XA and write down the corresponding equation. So if you write down the, to replace VA by delta XA, change aviation. Infinitesimally close. আমি প্রথম থেকেই বলছি যে infinitesimally close. Means you can have something like this also. See, this is any arbitrary vector. So you can take it to delta XA. What's the big deal about it? It's any arbitrary deviation vector, so you can choose it. This deviation equate all this delta XA. Right? So now just write it for. So what I'm doing, I'm just replacing VA by delta XA. And this is equal to RA B B UB UC the X B. Because VD is VA is delta XA, so VD B. Okay. And this we shall write it as K A B and where KAB and defining KAB. And obviously UB and UC, you know that this is the tangent vector. So this is, you can put a partial derivative also. Because XB is a function of tau. So to be more precise, you should put a partial derivative. Just to remind you that when you are taking this, H is fixed. Is it okay or this part is clear? Now let us go back to Newtonian mechanics. Let us consider an equivalent problem in Newtonian mechanics. So in Newtonian mechanics, let us assume that a particle of unit mass is subjected. Write it down. To write it down. You can remember, that is very good, but it is better that you just write it down. Let us assume that a particle of unit mass is subjected to a static, space-dependent gravitational force. So now what we are doing, we are considering an equivalent problem in Newtonian mechanics, Newtonian gravity. Let us assume that a particle of unit mass is subjected to a static, space-dependent gravitational field. Okay. So let us write down the equations for such a particle. Newtonian mechanics, this will be dt2, that is equal to unit mass okay. Vector sign we can get rid of. For convenience or simplicity of notation, you can get rid of this. So this is for a particular trajectory. Okay. A nearby geodesic will satisfy this is for a nearby geodesic. So you have a particle of unit mass whose trajectories are governed by Newtonian equations. They are subjected to a gravitational force. So you could know this kind of relation. This is the acceleration, that is the force. And now let, so these are two geodesics. Let delta xi be equal to, I have taken it to be x tilde I minus xi. This is what delta xi is. So these are two nearby geodesics. One is x tilde I, other is xi. Delta xi is the difference between the two geodesics. X tilde I minus xi. So if this is fine, then what we shall do, we shall take this term and make a Taylor expansion. So you can see that we are using the geodesic deviation equation. That is why it is the geodesic deviation equation. This equation is important. So what we shall now do is, we shall take del I by x and x tilde is basically delta xi plus xi, right? So we are expanding this about this is x tilde. So let us expand it about x. This is a small amount. So if you do that, this is because delta I x is the first term, and the second term will be plus delta xj plus higher order. Make a Taylor series expansion. Right? Because okay, so if this is fine, then let us go back to this Newtonian equation. Let us consider the difference I would like to tell you, or you should take it as a word of caution. Whatever I am doing here is a heuristic derivation of Einstein's equation. Because you should always keep in mind that you cannot derive. For example, if I say, is there a derivation for Newton's equation? You cannot derive Newton's equation, right? It is a law. So here also it is something like this, but some plausibility arguments you can give some kind of heuristic arguments by which you can actually get to an equation. This is something of that sort. So now what we are doing is we are subtracting this from this equation. And if you do that, this will give us tilde plus y x. So this we have already written down. Let us write it down here. Give us y x x minus g plus higher order terms. So I'm neglecting all the higher order terms which are of order delta x square. So we neglect those. So we have, so from here this and this will cancel. Ultimately, we have this difference is basically this. Okay, and this we shall call it, just writing it on this side. We shall write this down as Aij delta xg. Okay, so I am defining. So this is equal to this. This is by definition this. So let us identify what Kij is. So Kij basically nothing but minus del j del I. This is what Kij is. So you can see the similarity of this equation with the geodesic deviation equation. Can you see the similarity? Because earlier we had written down d2 delta xj or delta xi d tau 2 is equal to RABCD, then those things, whatever UB, UC and delta xd. And here also you can see that d2 dt2 x tilde I minus xi, that is delta xi, that is equal to something like Kij times delta x. So you can see the similarity. There you have RABCD, which is the Riemann curvature tensor. Here you have Riemann curvature tensor basically describes the gravitational field. Here you have this thing, phi x is the describes the gravitational field. Good. Okay. Let us now come to empty space. So what I am trying to say is that the equation that we have got in the Newtonian case, in the equivalent Newtonian case, looks exactly similar to the geodesic deviation equation. That is my question. So do you have any question here? If you have any problem with this claim, then it's clear, right? Fine. So now let us come to empty space. So in empty space, we have Laplacian of phi, nothing but zero. Okay. But what is this quantity? Empty space, follow? Yeah, I can, I also. Laplacian, so del I. So this is So this implies that in empty space KII is 0 because this quantity is nothing but KI. Same index ij equal to the I. Okay. Apart from sign whatever, this is KII is 0. Okay. So far so good. Everything is exact. What we have done, all arguments are exact arguments. There is no problem with this. Now we will make a jump. And this is why I say that this derivation is heuristic in nature. Let us make the jump. So I think it's a good place to stop now because you can ask questions. If you want to, if you have any doubt, you can ask question about this derivation. Otherwise, I will proceed. Any question from the IDSB or guys? This II obviously denotes the spatial indices, right? It does not have the time. Now, so for in empty space, we have KII to be equal to 0. This is exact. Now let us go to curved space time. So our first aim, by the way, is to find an equation involving these the geometric quantities in empty space. That is our first aim. We want to find the equation in empty space because empty space equation is the simplest. That is what we want to find. Curved space time. Here we make the jump. This is the jump. We generalize this equation. Generalize this equation to curved spacetime and write corresponding equation in curved spacetime to be this is a jump. If you ask me why have you made this jump, I have no answer. The heuristic derivation of Einstein's equation. So you have made this jump. Obviously, this is not a arbitrary jump. This is quite logical because you want in curved space-time, this was completely non-relativistic, right? So relativistic, whatever equation you should write, they should be covariant. So all the indices should appear. This equation cannot be an equation for curved space-time because it does not have the correct symmetry. But this equation can be a plausible equation in curved space-time. So this is equal to 0. So if this is equal to 0, then let us write down each expression for A be on top. What A B? Just tell me the expression. This was R A C E X B B tau. Right? This was the equation. So if the equation in free space, in empty space, in curved space, this is also empty space by the way. Whatever I am doing is empty space. So this is a generalization of this equation in empty space in the Newtonian case to curved space time. All this is in empty space. So if K is equal to 0, then you put D equal to A here. So let us see what we get. If I put D is equal to A here, then I will get R, A, B, C, A. Yes. Now you use the symmetry properties of the Riemann tensor. You know that this is antisymmetric in the last two indices. So you can take it here. A, B, minus. So this is equal to 0. The minus sign also goes out. Worry about the minus sign. But what is R, A, B? This is first and third index contracted. So this quantity is basically nothing but the leaky tensor RBC. Okay. So what we find is RBC DXB d tau DXC d tau is equal to 0. Since these are arbitrary vectors, tangent vectors, UB and UC are arbitrary tangent vectors, which implies that R C is equal to 0, or these are free indices, then write R A B is equal to 0. And this is the equation that you would expect to get in empty space, in curved space time. The leaky tensor is 0. Okay. So this you get from these arguments are quite exact arguments. Now you make a jump. This is the second step, the jump step. If you make the jump step, you immediately land up with the equation in empty space. And as you were pointing out that this is not an equation for the particle. This is an equation for the space-time itself. How the space-time evolves. So you have the equation for in empty space. And obviously you know that this RAB is a tensor equation first of all. It's fine. It's symmetric in AB. So there are 10 equations. So you get 10 equations as GAB. And this is tensor equation, and not only that, this is a second order differential equation involving G. That is what you want, because G describes the gravitational field. Therefore, any equation, if you write it down in terms of G, it should be second order. Yeah, the second order differential equation, and that is what we get. So it is all these arguments are plausibility arguments. These are plausibility arguments that this equation is a valid equation, or maybe a correct equation in empty space. Maybe, or plausible equation in empty space. Our next task is to find an equation where the space is not empty. This is our next. So we need to get the more general equation. But we could have said, okay, this RAB is equal to 0. This is the equation in empty space. Then why is this equation not plausible? Write this equation also. It is also a valid equation. The tensor equation. It's a completely correct equation. And if you see that, okay, whether this is second order in G, check it whether this is second order in G. The tensor equation, everything is fine. So why not? But only thing is that here you have 10 equations, this has more equations. Number of equations is much more. No, the number of independent components are same there. That's all. What I am saying is that all these statements that I am making, or the fact that the arguments that I have presented just now to come to this equation, all the arguments are, some of the arguments are exact arguments, and one or at least this argument that you have this equation and make this jump, write down this equation. Because I have not derived it. I have just made a jump and saying that if this is true, then in curved space time you write down a corresponding equation like this, KAA, where A includes all the indices. This is a plausibility kind of argument. It can be, it may be true. But then you could have said that, okay, let us not work so hard. Straight away write down this is equal to 0. It's also a possibility. This equation can also be correct. That is why I am saying from the beginning that all these arguments, this is a heuristic derivation. This is not a rigorous derivation. Not a rigorous derivation.
Stating the Riemann tensor 0 means there is no curvature.
There is no curvature. So even though that this you could have written that in empty space this is equal to 0, but then as Chom is saying is that if you say that my equation is this, nobody can stop you from writing this equation in empty space. It's a completely valid mathematical equation. The problem is, first of all, there is an economical problem. Number of equations that you have to handle here is much more than this. This is one economical problem. The second thing is that if you say that this is equal to 0, then your space time, you always, if you solve this equation, then you will always get a flat space time. You will always have a flat space time. That is the only solution. That is the only solution which is flat space time means trivial solution. So that is the only solution you will get. But solving this equal to 0 may not always give you flat space time. Flat space time means no curvature. So if Riemann tensor is equal to 0, it tells you that there is no curvature. So the only solution that you can get from solving this equation is a flat space time and nothing else. But if you solve this equation, so that is the reason that you reject this equation. So this equation, out of these two equations, this is 1, this is 2, you reject this. Because this will always give you a trivial solution, which is a flat space time, which is Minkowski metri. And that is not what we want. But if you solve this equation will give you a trivial solution, will give you a flat space time, but that is not the only solution. You can have a curved space time also, as we shall see in the future lectures. If you want to ask something, anyone? No question. Is it okay? Okay, so if all these arguments are so far okay for you, then now let us proceed further. We now want to derive the equation in the presence of matter. So let us forget about empty space and let us try to consider the case of matter. You have matter now. So in matter, if you have matter, then you know that in the Newtonian case, the equation is this is the equation in the presence of a matter. So you have sources which are masses, and this is the density. Load describes the density. This is a Newtonian equation for gravity. And we also know from our previous discussion that since GAD describes the gravitational field, we have discussed earlier that G naught naught is -1 -2 phi x. Remember this? When we describe the gravitational redshift, we derive this. So you see that the metric tensor, at least the 0,0 component of the metric tensor, contains this potential, gravitational potential, phi of x, which is nothing but minus gm by mod x. So we derive this, if you remember, if you go back to your notes, you will find this. So let us, in place of phi of x, let us put it, let us substitute phi of x in favor of g 0, 0. So if you do that, what you will get is Laplacian. This will be phi of x into phi of x from here will be minus half. So if you put it over here, Laplacian acting on this is a constant, so that will go away. So we have a minus half e 0, 0 that is equal to 4 pi gm x. We have this. Okay. Rho of x, you can write this as e 0, 0. I will come to this thing later. E 0, 0 is nothing but the 0, 0 component of the energy momentum tensor of a perfect fluid. I will discuss this later. But for the time being, please consider this. That what I am saying is that I am saying that T00 is rho. That is what I am saying. Okay. The details of what T is, I will discuss later. So that will solidify your understanding. But for the time being, just take this. That what I have done is I have written down the Newton equation for gravity in a different language. The language of the metric, one of the components of the metric tensor, and one of the components of the energy momentum tensor of a perfect fluid. Good. So this is the equation in the presence of matter. The earlier thing that we discussed was in empty space. So let me write down here that this is presence of matter. The presence of matter, that is equation. And our aim is now to find out an equation which is valid in the presence of matter. So what is the next step that I shall carry out? Can you guess what is the next step? Generalize to the curved space time. So let us. So now again I shall make a jump, as I had already made in the case of empty space. Generalize to curved space time. So how do we generalize to curved space time? We shall write down the equation and write it downstairs or upstairs. I have written it here. Jump. Okay. Again, why should you consider this equation? Does it look completely illogical to you? The answer should be no. Why? It is quite logical because this is the equation in Newtonian gravity. This is exact. So when you generalize to curved spacetime, it should obviously be covariant. So right hand side, at least it should be AB. All the time component and spatial components, everything should come. And also, if this is zero, if there is it is in the if it is in empty space, then you should get RAB is equal to 0. And RAB is equal to 0 is the equation for empty space. This is quite plausible. Again, this is a plausibility argument, and this equation should be, you should take it, okay, it should be true. Or this is the equation that should be there. Because if PAB is equal to 0, then you should go back to the equation for empty space, and then RAB should be equal to 0. And that is what you are copying. So this is the equation in curved space. Only thing that you need to determine is alpha. So what is this alpha? We don't know what alpha is. So we need to fix alpha. But before that, I told you earlier that this is the energy momentum tensor of a perfect fluid whose 0, 0 component is rho. Okay? This energy momentum tensor, you know that energy should be conserved, momentum should be conserved, right? So there should be a covariant conservation law for this energy momentum tensor. Therefore, if you take a DA covariant derivative of both sides, then by the covariant conservation of the energy momentum tensor, this should be 0. Okay, but by the covariant, so right hand side should be 0. But it turns out that the covariant derivative of the Ricci tensor is not 0. So this equation is not valid. So earlier we were sort of lucky. We got this equation, but this time we are not that lucky. Earlier also we tried to generalize from the Newtonian thing and obtain this equation. It's fine, no problem. Now also in the presence of matter, from the Newtonian equation, we try to generalize it to Cart's spacetime and write down an equation, but we are not lucky. This equation cannot be correct because right hand side is covariantly conserved, left hand side is not covariantly conserved. Because the covariant derivative of the Leakey tensor is not zero. The covariant derivative of energy momentum tensor has to be zero.
So, it can be said differently that the right hand side, that is not energy momentum tensor. That is some tensor that has zero component with.
No, this we want it to be the energy momentum tensor. Okay, perfect. That I will discuss later. I will write down this. We want it to be the energy momentum tensor because right hand side. Okay, go back to this equation. Equation at left hand side phi. What is this? This describes the gravitational field. Right hand side is key. This describes the source, the presence of, this describes the matter. This is matter. Given a matter, what is the gravitational field at a point X? If you write it, this equation, if you write it in this language, G00 is what? Is the 00 component of the metric tensor. So this side is basically a component of the line element. So this is geometry. This side T00 is rho. This side is matter.
So you can only say that to the energy momentum tensor if you consider these two noidal current.
Huh?
From the idea of noidal current, we say
That is why we are demanding that this is covariantly conserved. See, what we are doing is, this is an exact equation. There is no harm in this equation, right? But there is no harm in this equation. You are making a jump, again a jump. Mind you, I am not telling you that what I am saying is rigorous. It's a jump to this step. This side, if you make a jump, if this is T00, the jump should be covariant. So it is TAB. What is TAB? It is the stress tensor for a perfect fluid. But as I argued just now, that this equation cannot be correct. So it turns out that there is another tensor on the left hand side which is covariantly conserved. And that tensor GAB. So GAB is a tensor which is covariantly conserved. And therefore, let us write down or let us generalize this Newtonian equation that I am presently removing from the board. Let us generalize this equation this way. GAB. What is the GAB? GAB is RAB minus R. Write down all these pieces here. So this is the Leakey tensor, this is the Leakey scalar. It turns out that grad you identically, this is the Bianchi identity. I have proved it for you. So this tensor is covariantly conserved. So let us write down the equation now. In the presence of matter, instead of RAB is equal to alpha TAB, I am writing it as GAB. GAB is RAB minus this T is equal to alpha TAB. Now everything is fine. From the conservation point of view, everything is fine. Because the right hand side is covariantly conserved. Left hand side is a tensor that is identically covariantly conserved because of the Bianchi identity. So everything is fine. So I am saying that this equation cannot be correct. This equation can be correct. This equation can be correct. But there is no proof that this is the only equation. I'm not making any derivation, but But this equation looks to be good. At least from mathematical point of view, there is no flaw in this equation because all the conservation rules, everything, identities are being satisfied. So our next task is to obtain this coefficient alpha. So let us proceed to find this coefficient alpha. Before that, let me just contract the equation, this equation with GA. This is alpha. Okay. But this tensor is, by the way, it is called the Einstein tensor. This is RAB, half GAB. So GAB, RAB, that is once again the Ring scalar R minus half GAB, GAB. What is that? 4. Very good. 4 R is equal to alpha GAB, DAB, that is TAA. It's a trace of the energy momentum. This thing. The trace, because you lower indices or raise indices, you see the metric trace. So TAA, this is trace, this I shall call it to be capital T. Is that which denotes the trace of the energy momentum. So this gives us Q. So this implies that R is equal to minus alpha. R is minus alpha T. So what is the equation that we get? Therefore, RAB is equal to alpha AB plus half AB R. Taking this to that side. And now you can write this as AB plus R GAB. R is minus alpha B. Therefore, equal to get alpha common. GAB minus R. You can write this equation in this way also. So you have replaced this R by this. T is the trace of this stress energy momentum tensor or this stress tensor. TAB is associated with matter particles and fields, but it does not include gravity. All matter fields excluding gravity. Now the last step is, as I mentioned earlier, is to determine this factor alpha, and to determine this factor alpha, we need to see whether the proposed equation, this is our proposed equation, this equation reduces to the Poisson equation. We have to check whether this equation reduces to the Poisson equation. So let us now consider, we assume that this matter described by this energy momentum tensor, TAB, consists of static dust particles. Static dust particles. So what do I mean by that? I shall write this as EAB is equal to static dust particles. So I'm assuming that this energy momentum tensor, which describes the matter, the stress tensor, consists of static dust by static I mean that all the special components of U's are zero. That is what I mean. And dust particles means usually when I shall discuss or when you also attend the lectures on cosmology by Professor Mujumdar, you will see that this energy momentum tensor for a perfect fluid, it has a pressure term also. It is rho plus P UAUV minus P GAV. I have not written that exact form. But for dust particles, the pressure is zero. For dust particles, pressure is zero. And then that corresponding formula reduces to this. And you can see that T00 is basically rho U0, U0, and you can identify why T00 is equal to rho. So from question. So from here, you can immediately see that T00. Why? Because you want these velocities to be normalized. So U0 upstairs is 1. So T00 is rho U0, U0. U0 is 1. So you get T00 is equal to rho. This implies. And what is T0I? T0I 0. Because UI is 0. And obviously T0I is 0. Ij is also equal to 0. Ij are all these special these are the special indices. Therefore, you can set A to be 0, B to be I, this is rho U0, UI, but UI is 0. So these are 0. And what is this P? The stress of the stress tensor. This is what, by the way, this is called stress tensor or energy momentum tensor. I've written this. What is T? Is this? If you simplify this, you will see that this is equal to, okay, all other components are 0. See, it's simple because this is summed over AB, but all 0I and ij components are 0, so only 0 components are 0. So this is G00, P00, and from here you can write this as this. So fine. And this G00 go, P00 upstairs is go, and this is approximately minus. Because G00, if you remember, that is -1 -2 phi of x. So approximately, if you neglect phi of that 2 phi of x, G00 is -1. So what I am saying is that the curved spacetime is very close, deviates very slightly from the Minkowski spacetime. So this is approximately G00 is -00 is -1 is minus. Okay. So the offshoot of this calculation is that the stress tensor is minus. So you know what this is. You know what that quantity is. Is it okay? Is this okay? Are you getting tired with all these arguments? Post please see guys. Post see you are following. Okay. It's okay. So if you have any doubts, you can ask me because this is quite important. And all the arguments are quite physical arguments, but they are quite involved also. So you should be very sure about all the arguments that we are using. Okay. So now the last bit that we have to come, that we have to see, our aim is to find alpha. For that, we need to see that this proposed equation should reduce to the Newton's equation of gravity. This is our aim. So for that, let us go to the weak field limit. Weak field limit means Newtonian limit. We have already used the weak field limit here once. Because G00, we have replaced it by -1. So that is the weak field limit. So let us again use the weak field limit. So in the weak field limit, what will happen is, if you use the weak field limit, then immediately you can simplify the Riemann tensor. How can you do that? RABCD will be minus del D gamma A C plus del C gamma A. Correct? Is this okay? In the weak field limit. Why? Because the other two terms are the product of two gammas. But in the weak field limit, product of two gammas negligible. Because they are of the order of h square. So these are only terms which are of the order of h. I hope you understand what do I mean by h. What is h? What is h? Product of two gammas I am saying is of the order of h square. What is h? Only h is what? So by h I mean that AB. Remember I wrote down this equation once of the weak field limit. This is h. So if you calculate this, there are two products of gammas, two terms which involves the products of gammas. So gamma, if you use GAB to be equal to this, you know gamma is a derivative of G, right? So gamma is proportional to h. Product of two gammas means proportional to h square. Weak field limit h square, throw it away. Only these two terms are of the order of h. By h I mean this. Not the h that I wrote previously. It is the parameter which distinguishes the nearby geodesics, not that h. This h. Okay. So if this is fine, from here you can immediately write what RBD is. RBD just need to contract A and C, the first and the third index. If you do that, minus del D gamma A, C is A plus del A gamma A. Okay. Now, only we have seen that only this is equal to rho, this is non-zero, and all others are zero. So it is sufficient to look at the equation for R00 only. Because rest will be what? Rest will be R is equal to 0. That is the empty space equation. That is fine. Only this is 0. So just look at the R00 component. So if you look at R00 from here, let us concentrate on R00 component and consider that equation. Then you will see that this will be del 0 gamma A 0 A plus del A gamma A, right? So I'm considering the 0, 0 component of this equation in the weak field limit. Okay? Good. Now you will see that in the beginning I have said that the gravitational field that we are considering is static. So this term is 0. So this is a time derivative. So 0. So this is 1. So this is equal to nothing but del A gamma A. Since the gravitational potential is static. Metric tensor does not involve time. The metric tensor is not a function of time. So what do we get? Let me write down the equation once more. R00 is equal to del A gamma A. Okay? Now this you can write it down as 0 gamma 0 0. Static. R00 is nothing but del I gamma I0. Zero is I minus A. This you get using the formula for the Christopher symbol, symmetric affine connection, terms of the matrix. So I've written it in terms of the matrix. Once again, we are in the weak field limit. So what you can do is you can write this as approximately minus half. Then replace this Gij by eta ij. Do that. Simply minus half del and since we are using mostly positive signature, this is a special thing. You can pull it down without any cost of time. This becomes del I G0. So we have R00 is minus half del I G0. That's it. বল এই স্টেপটা এখান থেকে এইটা আমি বিগ ফিল্ড লিমিট করছি তাহলে আমি জি আই যেটাকে এখানে এটা এই যে করে নাও এটাকে কনস্ট্যান্ট এটা বাইরে বার করব ইন্ডেক্স লোয়ার নিচ করে নাও এর একটা ডেরাই এরকম হবে পুল ইট ডাউন হ্যাঁ হ্যাঁ তাই তো লিখেছিলাম প্রথমে এটা লিখেছিলাম কিন্তু you can pull it down because of the signature that we are using. Mostly positive use করছি and take it down. But what is del I? Find out this I is summed over. This is equal to minus half Laplacian আর G00 টা আমি লিখে নিই এখানে G00 we have already used once is this, right? So if you put this G00 here, what will you get? This is equal to Laplacian of G00. This is when the Laplacian will act on this. This is 0. So minus 2. So this will be what?
Yes, sir.
Del square R. So R00 দেখো এটা থেকে শুরু করেছি R00 weak field limited ওইসব কায়দা করে R00 is ultimately Laplacian of R. সুন্দর এসে গেছে। So let me write down this equation on top. Our aim, by the way, is to see whether the proposed equation goes back to the Newton's equation, Poisson's equation. We have R00 is equal to minus Laplacian of x. That is what we have got. This is our proposed equation. It has 0, 0 component in our side. All other components are 0 because this is 0. So 0, 0 component of this equation is nothing but R00 that is equal to alpha E00 minus half G00. What is T00? T00 we have already obtained. What was T00 downstairs? Anyway, that doesn't matter also. And do it another way also. Because you can write R00 as alpha 00 minus half G00. Let's take all the indices upstairs, but this is approximately down. Let's check that in the weak field unit. This. Now this is equal to from here equal to alpha T00 is 0 minus half T00 is minus 1 approximately weak field unit because we are neglecting that term. And what is T? T we had calculated earlier. What was T? If you look at T, it was minus rho. That is what it is. From here, therefore, you will have alpha, this minus and this minus plus. So rho minus rho by 2 is rho by 2. This is rho by 2. And R00 we have already computed, that is grad square of x. R00 calculated. So I'm substituting R00 is equal to this, and that is from right hand side is equal to this. But from Newtonian gravity, grad square phi of x, this is Newtonian gravity, 4 pi Gn rho of x. Therefore, if you this and this must be equal, from here you get alpha, this is like alpha, rho cancels. Therefore, alpha is 8 pi Gn. So only if the constant, the value of the constant is 8 pi Gn, then this proposed equation goes back to the Poisson's equation of Newtonian gravity. And therefore, now our equation is here. Obtain the proposed equation. The proposed equation is RAB R GAB R. This full thing is Einstein tensor GAB, which is covalently conserved identically 0. And under a covariant derivative by y and k identity. This is equal to 8 pi n gn is the universal gravitational constant. 8 pi gn and if you restore the speed of light, then you have to divide this equation from dimensional consideration. If you restore the speed of light, you have to divide it by c to the power 4, and therefore your final proposed chemical equation of general theory of relativity or gravity. And this equation is an equation which is second order in the metric tensor GAB. This is a tensor equation, and there are 10 such equations. This is a second order differential equation, nonlinear differential equation, obviously. Is a second order differential equation, it's a tensor equation, there are 10 such equations, and also it reduces to the appropriate equation in the Newtonian limit. Reduces to the Poisson's equation of Newtonian gravity. And this is the field equation of proposed by Einstein. And later on, he proposed another term. He added another term to this equation, and that term is minus lambda, where he said that this lambda is a cosmological constant. On the left hand side, he added another term which is minus lambda Ga. This lambda is said to be a cosmological constant, and you can see that this is a term which you can obviously add to the left hand side, because the left hand side is still covariantly conserved, because by the metricity condition, by metric compatibility, covariant derivative of GAB is 0. So this is also a valid term that you can add. There was a particular reason why Einstein added this term, and that reason maybe I can also discuss with you later, or maybe it will be discussed when you attend the cosmology course. But you can roughly understand why Einstein added this term. There was an observation at that. First of all, this is a proposed equation, and proposed equation. See, whatever arguments, these are all heuristic arguments. Kind of, some arguments are rigorous, some arguments are heuristic, and then you land up to this equation. But the only check whether this equation is correct or not or incorrect is that this equation must be able to explain observations and also predict something new. Any good theory must be able to predict some new physics, and also should be able to explain some of the things which were not being explained by the previous theory. So it turned out that this theory was able to predict and also able to explain some of the things which could not be explained from Newtonian gravity. So that is why later on people realized that there must be some truth in this equation, and this is the correct equation which describes gravity. But then Einstein thought there was an observation by Hubble, 1929, around 1929. Hubble observed that the universe is expanding. From the motion of the galaxies, he observed that the universe is expanding. And Einstein got to know of this observation that the universe is expanding. But he basically thought of adding this term to this equation to get a static universe. He wanted to make the universe static, so the universe does not expand. But then Hubble's observation came into the picture around 1929, and that observation told that the universe is expanding. But Einstein's idea of adding this term was to make the universe static. But when Hubble's observation came and we learned that the universe is expanding, then Einstein said that adding this term to this equation is one of his greatest blunder in life. So this cannot be correct. But his greatest blunder also turned out to be his greatest triumph, because if you add this term, then only you can get to solutions which are expanding. He added this term to make the universe static. That was his idea, to get a static universe, because he did not want he was not in favor of an universe which is expanding. But then observation said, he added this before the observation. Observation said that the universe is really expanding, and then he said his statement was that this was his greatest blunder, but it was not his greatest blunder, because if you add this down, you get solutions for a universe which is actually expanding with a positive line. Okay, so let us end here today, and you go through this derivation of Einstein's equation very carefully, because this is, and now you can realize that this is really the equation for gravity. This is not the equation of a particle. But to get to this equation, you have used geodesic deviation equation. Also various things, various tools like Newtonian limit and everything. Geodesic deviation equation is one of the equations which is important. Getting to this equation, I don't know whether Einstein got to this equation by using the geodesic deviation equation. That I'm not sure of. Then I have to look into the original paper whether his argument was also through the geodesic deviation equation. But I think his argument was not like this. This is a modern way of understanding probability. But maybe his argument was also like this. So you have to look into the papers. That is up to you. This you can take it as a project to find what was Einstein's original argument to get to this equation. This is the equation in the presence of matter. Last thing that I would like to say is that this equation should go back to the equation in the absence of matter. What is the equation in the absence of matter? RAB Vicky tensor is equal to 0. In the absence of matter, TAB is 0. This is 0. So Einstein tensor is 0. So this part is equal to 0. And from this equation, if you contract with GAB, you will see that R is 0. And therefore, RAB is equal to 0. So in the absence of matter, you really get back the equation that I wrote down in the absence of matter, which is Vicky tensor is equal to 0. This equation is the equation for gravity and not the equation of a particle, but to get to this equation, you are using the equation of a particle. You have used geodesic deviation equation, and in geodesic deviation, to derive the geodesic deviation equation, you have used the geodesic equation. So all these equations are important. But this is geodesic equation or geodesic deviation does not tell you anything about how gravity itself will evolve. This equation tells you how gravity evolves, how the geometry evolves. The geometry is also changing. So this is the equation for that. This is not the equation of a particle. Okay. So let us stop here. And next Monday, from